How's it going, everyone? Alberto Gonzalez here, exploring right now the RxJS, this library to help us to think and work with observables. And it's interesting to understand how do we get here, because this is much of a bigger uh, course that it all starts with Redux, the basics of Redux. What is Redux? This API that allows us to now model state change, and by exposing it as several methods from an object, such as dispatch, subscribe, among others, we slowly but progressively look at how this way, in this case, this flux architecture allow us to have now predictability when it comes to update the state, because we don't have that natively on JavaScript, and we need to know and we need to have that. So because this is a concept that also comes from functional programming, the end goal of Redux, at least from one of the maintainers, the design and the intent and philosophy behind that, is make the state management maintainable by using is now some of this concept from the flux architecture, by using is now actions and reducers, and incorporate slowly but progressively the predictability and serializability that we need in our code, especially to handle all of these different state change. And why it's important to have now an understanding of concept like immutability, to understand what's going on behind the scenes. So not only that, but also by following is the flux architecture to make that happen, and by creating now is unlike flux where they define is now all of this different state in one single place, or in this federation of states. Now we have one single place, one store, where we can define all of our states, followed by the actions that we can now update in our state, or in other words, the reducers. And now how the reducer actually work behind the scenes. Also, the idea of Redux is to keep your state your state update separate from the asynchronicity in your programs, and by slowly but progressively understand some of these concepts in functional programming, which is part of the intent of this, is that hey, this is how we need to use some of these concepts, for example, like monads. Again, I just only know the concept of monad is based on how do you put it? Based on and it is functionality, hey, a monad is a way to describe is a state change. So Redux is kind of that. And also concepts like functional programming is like point three in arguments, data points, list operation, which is something that we need to later on use or see more in depth, as well as the immutability, which is the idea that we need somehow is a data structure to keep up the state change in an object, and return always is a new state out of that. So that's very interesting, as well as some other advanced concepts, such as now the synchronicity, how we're gonna handle our synchronicity in our programs, where this is what we getting here in by looking at RxJS. So because the idea is to keep the state update separate from the act of updating an state, or the idea is to keep the asynchronous behavior from the state updates. Now, that's why in Redux we have something called metawords, and they use now this idea of thunks. And we need to understand what thunks is by revisiting and understanding that what is the main problem that we as a UI developers need to deal with. And that is that not only by writing its own application, using is now this object paradigm, which is like fish in the water. A lot of us don't understand how all of these things come from, and we just give that things by settle. But it's understand that this object programming, what it does is to try to now put the data and the functionality into one single bundle. And this is there is a very interesting interview that the pragmatic engineer YouTube made to Grady Butch to understand now how all of this came from. And it all was from after the Second World War, where he described that now computing in 20th century was woven in the loom of despair. I think it is. I just want to woven loom meaning. I'm not sure what loom means. Okay. Woven. So the history of computing was woven in the loom of in the looms of sorrow. In the loom of sorrow. Woven in the loom of sorrow is a quote that refers to the history of computing being shaped by conflict in computing, in turn changing the nature of warfare. I think this is a concept that comes from exactly, that's interesting. Grady Butch mentioned that and this kind of thing is important to understand.
Grady Butch is one of the country's most prolific minds in software. He has been for many, many years. His work with the unified modeling language, his own ongoing contribution to the development of both the theory and practice of software with his handbook of software architects and skills in software are part of shape, both in form and substance. Grady
one has influenced the other. Today we're going to look at one specific element of that, one part of the human experience, namely the coevolution of computing and warfare. Our story begins in what we in the West would call the Middle Ages, although in the Islamic world this is the Golden Age. So let's come to a moment in the city of Baghdad on the east bank of the Tigris River, where we find a place called the House of Wisdom. Here was a place of learning, of meeting, a place where cultures could come together with acceptance of one another, and where mathematics and science began to flourish. One man in particular, Muhammad ibn Musa al-Khwarizmi, was at the center of a lot of this work, and it is from him We have the ideas that come from the Hindus that lead to modern numbers, the Arabic numbers.
But again, this is not an historical video. It's just a way to, because he goes way back at a time to the Middle East, to the Middle Age, with circa 11th, 12th century BC. But again, I don't want to go down deep into that road. Just want to describe that at that particular podcast he described is that interviews with the Pragmatic Engineering YouTube channel about now how, for example, especially for computer science in the past 20th century, how the computing was woven in the loom of sorrow. And because now, back then we have programming languages like more close to the machines to understand what are the kind of instructions we wanted to use and describe to tell them, hey, this is what we want to do. This is how we're going to move this register to another place in our memory. Similar like you have a drawer. All right, hey, I want to move this pair of sockets to another position in my own drawer. And then I can now add more or remove some of these socks in there, and then starting to now computing upon that and apply some of these basic mathematical operations, the arithmetic, and this is quite interesting. But in any case, because in the late 50 and 60, language like Fortran, which is quite interesting. So Fortran here, the name description. So Fortran is the formula transcriptions, right? So it's a high level programming language that it was now the beginning of, and it was originally developed by IBM, this industrial business machines. So Fortran was that kind of language that we don't need to actually know all of this intrinsic low-level stuff to actually move register from one place or another, like in an assembly, but is now a more human way to describe our programs. And this is also part of the computing or programming specifically, is that we are now sharing ideas and describe how that things should be to others. And there is now a side effect of telling that to the machine to do that kind of stuff. Because as computer now starting to evolve, and people back then in the 60s, and again, this was slowly but progressively movement towards the computer science, and then look now that as a business, and how can we now provide some of these solutions to initially to the Defense Department, where now is when all of this scalability problems and complex applications actually come up. Like, hey, we need to now find a way to write all of these programs in a way that makes much more sense for us. So when we can now bundle the data in its functionality, because programs like Fortran were the first golden age of computing, according to Grady Butch, is, hey, we now can have this particularly, so we can decompose systems in an algorithmic way, which is a great thing. But this then in something that, as the community evolved to deal and face reality, and how can they translate some of these requirements into business operations, into something that is economically sustainable and interesting, programming's language like Ada, which is now an amalgamation of all of this stuff that we give by settles, like the opportunity programmings, and is that now, slowly but progressively, with the rise also of another language like Smalltalk and all that kind of stuff, which is again something that he mentioned here, and I think let me actually, so Grady Butch, the evolution of software architecture, okay, especially in this, it's quite fascinating. It's very,
Decades.
very,
Where I'd
very
be
fascinating.
parachuted in, the customer would say, "Come help me, Mr. Wizard, with this particular architectural problem." And the exciting thing about it for me is that for many decades, I was engaged in projects across every conceivable domain. And I'll pause there to say that roughly around the turn of 2010-ish is when I began to be drawn back into the space of AI.
So when you say you worked on legacy systems, what does a legacy system mean to you?
Well, the moment you write a line of code, it becomes a legacy system until you throw it away.
Yeah.
So all code to some degree is a legacy system. Facebook is a legacy domain. Google is.
But then
The
again,
presenting problem for software systems was they were generally not distributed. They were largely monoliths. And how could we build larger and larger systems that were sustainable and economically interesting over time?
and this is part of the reason of why we are actually looking at this kind of code like JavaScript, specifically at the asynchronicity, because first we are not only going to be able the main role of UI specialist is not only to write and design this kind of system, which is of course important, but also to maintain, and also is to now make it make those applications interchangeable in each other's. So we don't only focus on the design, the maintenance, which there is a lot of things going on, the design, the maintenance, but also is the distributed computing. And that is why we're slowly, or why at least in this course, we went through how can we now in JavaScript deal with this kind of challenge, especially the concurrency of application or tasks that overlaps at a time. Okay, so I don't want to dive deep too much into the history of this, because again, what is relevant for us is to jump in straightforward to the RxJS. So again, as a way to now understand or to be on the same page, again, fair use, to be on the same page here with how do we get here to understand the RxJS? Well, we need to understand a little bit of history, a little bit of context of that. So that's quite interesting, and I am not here to because a lot of people, when they hear about Fortran and COBOL, they actually come of the words from that. It's like, hey, I don't want to write in this programming language because they are old and there is no market share for that. Both of them are true, but it's important to understand that most of those applications that you are like to use in today's world or language, at some point you will have to face what those others all language actually face, which is the entropy of the use application. But in any case, again, this core is focus is on the asynchronicity and how do we handle that. Now,
well, the golden age of that first golden age of software engineering began to change as we started to see the rise of distributed systems.
And that's important at least to have that notion, the first golden age of that.
And that rise, again, happened not in the commercial world, but it happened in the defense world. The ARPANET was, funded by the government, funded by DARPA. I was, as I mentioned to you earlier, I got my first email address in 1979.
The golden age
was through algorithms. So I alluded to a phase I called the first golden age of software engineering. This is the realm of the time of functional, or not functional, but algorithmic languages such as Fortran and COBOL, APL, Lisp, and the like. Although Lisp was sort of a multimodal kind of language. But the dominant...
But it's interesting because here this is the first golden age of the internet, the first golden age of computing in the 20th century.
Way that we decompose systems was through algorithms.
Exactly. And this is just elaborating is how actually, as well, I don't want to stop that because I prefer to the Grady Butch elaborate this.
And so you saw the rise of structured analysis and design techniques, which made a whole lot of sense at that
fair
time.
use.
This is where you had the Jordans and the Marcos and Constantines and the like, because the presenting problem for software systems was they were generally not distributed. They were largely monoliths. And how could we build larger and larger systems that were sustainable and economically interesting over time?
Pause. This is fair use. This is also the reason of why I'm exploring this kind of ideas and why right now as JavaScript developers we have inherited all of this kind of stuff, and it is up to us, and that's the next level of competency, not only to describe all of this kind of stuff, but actually is when you need to provide the services or the value to others, know what you gotta do and understand the complexity. So once you understand that, you will embrace it. So I think this is quite interesting to elaborate, to describe is the first golden age of programming, where back then programmers worry more about is how do we now create more monolithic or applications that are economically sustainable and interesting. And the way to do that is by using now this algorithm. So decompose systems in this algorithmic way. And that's why back then we worry, still do, about the algorithmic analysis, like big notation, design of your algorithms, because resources weren't that available like we have in today's video. Or like we have in today's, at least in 2024. So all of that is just to understand that back then in that first era, we didn't have anything related like objects or all that kind of stuff, which is now we are in the fish like in the water. It's like, hey, you are actually breeding in the same ecosystem that all of these different persons, including Grady Butch, actually have to develop over time to come up with some of these solutions to, again, make all of these applications, these monolithic applications, economically interesting and sustainable. And then with the second golden age, according to Grady Butch, of computing is when the rise of this distributed computing. Again, this is something that happened is on the defense world first, not in the commercial. And and this is when we have like ARPANET, which is initiated in October 1969, and with the email services with Grady Butch, as Grady Butch mentioned. And go.
Well, the golden age of that first golden age of software engineering began to change as we started to see the rise of distributed systems. Mm-hmm. And that rise, again, happened not in the commercial world, but it happened in the defense world. The ARPANET was, funded by the government, funded by DARPA. I was, as I mentioned to you earlier, I got my first email address in 1979 when there weren't that many email addresses
Oh my
around.
God.
In fact, one small story there, when we had the ARPANET in the air, I was teaching at the Air Force Academy at the time. We had a little mimeographed document that listed the email address of everybody in the world. I think at that time there were a few thousand people, so we knew who everyone was at the time. It was pretty cool to go back.
Fair use.
So the first distributed systems were happening in that domain. Indeed, back to Vandenberg, I worked on a system called the Telemetry Integrated Processing System, which was a close network of some 32 mini computers. Mini computers were beginning to be a thing. And so the problem
where many computers were a thing.
of how do I deal with taking a larger system and breaking it up into multiple distributed parts was beginning to emerge as a problem. Hadn't reached the commercial sector yet. So the industry began to see that there were limitations to what one could do with algorithmic decomposition. And so there were these pressures all around to try to attend to the next kinds of software that was distributed, software that was real-time, software that was multilingual, software that worked on a variety of computers. And I had to deal with all the normal aspects of distributed systems, which is they're going to fail at various times, and I've got communication issues and the like.
But this is quite interesting, which is exactly why.
And so there were these pressures all around to try to attend to the next kinds of software that was distributed.
For example, in this particular case, and that's what we really care now on the commercial world. So the commercial, why developing this kind of application, right? In React or in any other frameworks, what we really care about is that, hey, all of these different kind of systems that we are building is not now monolithic. They're not going to live inside of those particular computers. They're also going to be shared that. And you, for example, in the case of the web, you're not only going to share that document, but also it is functionality, and also it is code that brings this interactivity to the user, which at some point we are doing. At some point we are be one of them.
Software that was real-time.
So for example, this kind of thing. So how can we handle is now distributed computer software that is real-time, and there are some particular ways of or protocols that allow us to do that. So for example, WebSockets, and now with the rise of another protocol like the HTTP3 and the web transport and the WebSocket transport, where now is reduce the amount of communication that needs to happen, so it make it much more straightforward. So real-time communication.
Software that was multilingual.
Software that is multilingual. So now is not only language exactly, server and client side, based on this architecture. So the client is running on the server. The client is running on The client is running on particular language, JavaScript, HTML, and CSS, and on the server we have is PHP or Python or Perl, so multilingual
software that worked on a variety of computers, and
software that works on a variety of computers. That's interesting. So not only whether it is Windows, Mac, right now here, Windows, Mac, and Linux, where Mac and Linux has the same predecessor. But this is interesting to understand what was the challenge and the current challenge that we need to handle. All right, about this distributed computing, and which is the reason of and the rise of this cloud computing. It's like none of these things or the application that you're gonna build now is gonna, as a huge company, they're going to expose some of these different computers, servers you may like, and now you can have access to all of these different services and find a way to make find a way to now have an architecture to help you to come up with some of your problems, especially for startups or for any particular company. But this is quite interesting and also quite complex, because with this rise of distributed computers, hey, I want you to this server actually now handles the database, and this is the image that I upload and someone downloads, and this now about the authentication, and this another server about the catching, and this another the gateways and all that kind of stuff, you know. So each one of those different computers, actually now we are in this era of this distributed computing, and again, this is because it is economically interesting and sustainable. I'm not sure if that is economically sustainable, because you are now putting or betting you're putting all of your eggs in one baskets, especially with Amazon and Microsoft or Google, whatever it is. But yeah, this is the risk of now developing this kind of applications on top of those different platforms. So
I had to deal with all the normal aspects of distributed systems, which is they're going to fail at various times, and I've got communication issues and the like. So it led to a realization that we needed to think about software in very different ways. The other thing that was happening is in research, you saw the rise of languages such as Simula and Smalltalk, which were looking at the world in fundamentally different lenses. So here we are again in the late 70s.
Simula and Smalltalk were different now. Again, this is when the rise of this object-oriented programming patterns.
And again, I'm a 20-something. I was asked by one of my former teachers at the Air Force Academy, say, Grady, would you go help the Department of Defense figure out how to use this new programming language called Ada so we can apply it to modern software engineering techniques? Now, why was the government worried about this? By that time, software was a real problem for the Department of Defense, actually for all of the federal government, because there were several thousand languages in use that exploded because Fortran and COBOL were useful for some things, but not for all things. And so there was a decision made to build one language to rule them all, and that was the Ada programming language. Ada was far ahead of its time. It was a language that was influenced by Simula and Smalltalk and others, but used the ideas of abstract data types from Liskov and Gauguin and others.
Abstract data type, you know, is a mathematical model for data type. Okay, abstract data type. It's a mathematical model for data type, defining its behavior from the point of view of a user of the data. And this is now when the rise of this object-oriented programming came here. But this is a mathematical model. Oh, ADST was first proposed by Barbara Liskov. Shout out to Barbara Liskov, bro. Jesus. And Steve N. Seil in 1964 as part of the development of the CLU language. Algebraic specification was an important subject of research in CS around 1980 and almost as synonymous for abstract data types. But again, this abstract data types is a mathematical model for data types, defining its behavior, semantics from the point of view of a user data. And that's quite interesting, especially in terms of possible values, possible operators on the data on this type, and the behavior of this. this mathematical model constructs with data structure. Constructs with data structure, which are concrete representations of data, rules, and can be concretely implemented using either a list or an array. Another example is a set which stores values without any particular order and not repeated values. Values themselves are not retrieved from sets. Rather, one tests a value for membership to obtain a boolean of this. Exactly. This information hiding strategy allows the implementations of the model to be changed without disturbing the client programs. But the model only informally defines an ADT, an abstract data type. The notion of abstract data type is related to the concept of data abstractions, important in object programming and designed by contract methodology from software engineers. But
use the ideas of information hiding from David Parnas, all ideas that were very new at the time, but frankly are part of the atmosphere in which we breathe right now. And so as an industry, we really didn't understand the methodologies to make that work. Thus was born the Booch method. I was in 79 till about 81. I was going back and forth across the United States, helping the federal government and helping contractors try to apply this new language in new ways. And this was the beginnings of the second golden age of software engineering, in which it was not so much the complexity of the algorithms, but it became a systems engineering problem, systems that were dealing with distributed systems that were very new at the time. And that was the essence of the Booch method. It was the things I learned about helping organizations architect systems with these new kinds of domains and new kinds of languages.
Could you explain what the Booch method is? I understand it has to do with object-oriented programming, but coming from you as the person who invented it, it would be nice to explain what it is and why it was important.
Well, let's go back to Plato. Talking about going way back, I wasn't around then, but I've read about him a little bit. There's this wonderful treatise he wrote, a dialogue, in which there's a debate about how one should best look at the world. Should I look at it as atoms, or should I look at it as processes? Well, the first golden age of software engineering was more focused upon the processes, the algorithms, but there's a parallel way of looking at the world, and that's looking at it through the atoms, if you will, the classes and objects within them. So yes, I was influenced by abstract data type theory, by Plato, by a lot of other interesting philosophical things that were coming together at the time of looking at the world in fundamentally different ways. So the Booch method was really trying to codify that. How could we decompose systems not based upon algorithms, but how do we decompose it based upon classes and objects? And again, that's where I was influenced by Liskov and Parnas and Dijkstra and Hoare and the like.
So, but in any case, to now get in, so now we make sense a little bit of how now do we get here in terms of the developing our JavaScript applications with Redux and React and all of these user interfaces that we need to provide to companies where they need to find a way to actually allow them to develop their applications or design their system as one and have the capability to add different change or remove is their features, and also help them to migrate at some point or do some code refactor, where now what you gotta do is to dive deep into those systems, and because we are not only writing is this monolithic application or this UI for this company, we also at some point needs to handle is this concurrency that happens in an application, this asynchronicity, this communication that needs to happen to other computer, this distributed computing. So because of that, well, we are not reinventing the wheel. There was a problem that was faced by a lot of programmers back in the 60s and the 70s when in the defense sectors they have to actually now with ARPANET deal with, hey, how can we now write applications that are distributed? Okay, we're gonna distribute the load of different computers, and how can we make that in real time? It's another one. So how can we is write them in a way that it makes sense for us as developers in given the rise of all of this multi-language, and so to bring back here again, in JavaScript, we have now several of these specific tools. And this course starts to understand that at least the different tools that we have now in our asynchronicity to handle the asynchronicity, aka the concurrency. Kyle Simpson is one of the software engineers that, shout out to Kyle Simpson, the structure of this. Right? And that's what's quite interesting. Absolutely, absolutely, totally, totally. So, so because this is an exploration quickly of how do we get here, especially to look at now observables in this RxJS, is that now in the language have, so the language per se provide is, it's not the language, it's actually the platform. The platform provides is a tool to handle is this kind of concurrency, or in other words, to put some computations to evaluate it at some point in the future. It's the continuation of this set of instruction to be evaluated after an X amount of time. So callback is something that the language provides for us, especially the timers, okay? And because with callback we look at the different problems that we can have. So for example is the how do you put it? Yeah, for example, the Jesus. Exactly. So, for example, on the with callbacks, the problem is the inversion control. Is that now you're passing is a set of instruction that you don't know when they will fire. So of course this generates some of the trust issue. So because you just assume that those set of instruction will run is not too few times, not too many times, not too late, not too early, don't solve errors, preserve the data context and all that kind of stuff. So, of course, callbacks also have another trade-off, which is they are not reasoned about, especially as we as humans now write our code, which is in this sequential blocking way. We are not able to follow, it is quite hard to follow that. Now, that's why we have another tool called Thongs, which is originally, it predates JavaScript, and this just the value proposition of Thong is that, hey, that's going to eliminate time as a complexing factor when dealing with this asynchronicity. How so? By now giving it a function everything that it needs, especially synchronous functions, everything that it needs, and we're going to wrap that into a function, so anytime we call that we get that same value. So this is great because now we can is now referencing that in memory, and anytime we actually call that in memory, we're gonna get is the same value. This will act now as a token for that. So if you think about now in terms of the asynchronous programming, okay? So instead of actually, so it's the same as synchronous, but you're gonna have now this function, and you're gonna pass everything that it needs to, and by the time that you get that value, you're gonna pass now a callback to get the value out of this. This is how you can actually create now thunks, and it makes a lot of sense of why this the maintainers of Redux actually implement now thunks to actually handle is this concurrency. So they don't. So they eliminate time as a complexity factors to deal with this task that can this asynchronous task. Now, then we look at again some of the trade-off of thunks, which is, as I mentioned before, however, it doesn't solve the inversion control, and that's when now promise kick in, and this is a counter that comes from the programming language called E. One of the TC39 members actually some of the creator of the programming language called E, called Mark Miller. They say, hey, this is something that we have in this language called features. So let's go to now propose that on the language. So that's why now promise lends to the language. And the value proposition of this is, let's go to now is bring this trust to the language for handling is this asynchronous operations that with thunk we didn't have that guarantees, like, hey, we're gonna make sure that this works, that this async operations, when you fire up an Ajax request, it'll be run only once, okay? But you're gonna have now the certainty that it will run too often, too late, too slow, too early, don't solve error, gonna preserve the context. So you can think of this promise as the callback manager, so an event listeners. So promise, the value proposition of this is, let's go to now, we need some sort of placeholders, so we need some sort of placeholder to eliminate time as a concerning factors, wrapping around a value, okay? And for that, well, there are several methods that you can look at that. For example, .then and .catch. And even though that you pass some sort of callbacks, you have now the guarantee that this will run as it is. All right, with all of this previously guarantee that I mentioned before. Now, this promise is not only is a mechanism for data control, flow control, but also for data flow. And here is where we started to see, for example, point-free functions and all that kind of stuff. Again, we're not going to dive deep into the functional programming because what we care about is to jump straight forward to observables. So promise help us this inversion control problems, and also provide some of these abstractions that are commonly used when you fire Ajax requests. Okay? So such as the all settled, any, and race, and how now race say, hey, whoever, based on this entire collections of promises, I want to give you is the first that resolve or reject in the case of race. In the case of any, it's like, hey, we're going to give you the first that resolve and short circuit the rest. All settled is say, hey, I'm going to give you is all promise settled, whether it's rejected or fulfilled. and it's gonna give you into a nice little object where you have the status. You need to check the status. This is rejected or fulfilled. And the promise at all would say, hey, I'm going to evaluate all of these collections of promise and resolve if all of them are resolved, or reject if any of them was rejected. So the idea is, with this set of abstraction or this set of method, is to help us cover most of the common use cases. Now, in terms of this next things called generator, where the idea is that the value proposition of generator is that we need to find a way to model is state machines. So generator is the syntactic form that allows to describe that in the language that come from Python, according to Kyle Simpson, one of the creator of the You Don't Know JavaScript book, which was quite interesting. And the way how generators work is by now give us the ability to, unlike normal functions, when you run to completion, you now get into this function until you find a yield keyword, pause, freeze everything here inside of the function without blocking the main thread, and then now return or pass control to whoever call that generators. So you have, and then at some point in your program, you can call the generator to get in and resum that. So this is pretty much like a video, like a YouTube video, when you play and pause that. And you pause that indefinitely until some actor came in and resume. Now, the other is, as we explore how generators works, and when you now use a generator, it gives you now this, or when you call a generator to create this series of steps that is not going to run to completions, and since the idea of this is to in JavaScript with generators, is we have now the ability to we have now the ability to is which is one of the important property of the function, is that, hey, no one here inside of this function can preemptively interrupt this with some sort of instruction. You can call functions here, and then you have now the call stack where you're going to add all of these function calls until you, of course, or reach to the end of that function evaluation, or until that function reach to completion, or you can Stack Overflow that, right? Now, but this is something that this is known as a cooperative concurrency. The idea of this is, by looking at how we can use generators to not only, as the name suggests, is generate a set of values. When you create your generator, you're creating is this set of flows, set of instructions here, and it's gonna give you now an iterator, which is that is a pattern for typically stepping through data. But in this case, we're gonna walk through this series of steps in our generator. So we look at how can we do that for generating values. The more interesting is that how can we use that as a way to now pause and resume async operations, right? And we look at that, and that was very, very interesting. I think the next level of competency for JavaScript developers is to be able to do that and describe that So if promise solves the inversion control issue, generators solve the non-sequential and non-local reasoning. So generators and promises are a great tool that we have in our language, but this is for handling is one asynchronous operation. So what happens when we now our event source, whoever is sending us these events, actually send us is an streams of data, right? So a promise here fell short, and if we try to use that, we end up having to now find a way to separate is the setup and the definition of the consumer for that, and then you have to create some sort of closure to actually keep up the promise, and then expose that, and somehow is now coordinate is which the amount of promise that you are creating, as well as the data that you are emitting. So all of a sudden you start from the beginning of handling is this coordination problem. So that's why now we have another things to think about it, which is, hey, instead of using promise, why we don't use now list methods? So list context to define each one of those stuff. Well, it turns out that again, with lists, we have the setup and the consumer on the same spot. So the idea here is that we need a way to now is model that based on an event source, each independent unit pass through a series of steps and then distributed to the system. So enters observables. So observables now give us that ability. So if you can think, for example, in arrays where this array is fixed and this is synchronous, right? So bam, you get it. With a streams of data, which is asynchronous, you don't know when this happened, but it will happen. We need is to actually is whatever that event came from an event source. So for example, click a button or type in or key up and key down modes, user events or server events. We need to have the ability to give me that single unit of data, apply some transformation or pass through series of steps so I can distribute that onto the system. So a real life example of observable is by using is a spreadsheet. So everybody loves a spreadsheet. Who doesn't? I do. I'm a gap. I'm someone that definitely love spreadsheet. I'm quite obsessed of using that because it gives you a lot of sense of control and order, especially if you want to organize some sort of trip, some sort of holidays, holiday trips, and all that kind of stuff. But in any case, here we are. Okay. So with observables, as I mentioned here, right? Observables, we don't have any native we don't have any native stuff in our applications, or we don't have any native support of observables in the language. So that's why we're looking now at this RxJS, which is something that was developed by smart folks at Microsoft, because they now, as you can see and as you can remember from Granny Butch, those people actually now have to handle those not only monolithics but also distributed computing. You know, and it makes a lot of sense for us to understand that is that all of these different computers that authentication and databases and caching and gateways, and how they can now handle all of these different data as they came here, okay, and do some common stuff, or apply some sort of operations. So for example, like sampling is that all of this data that I'm getting from this service and this another server and this another server and this another server, how can I now is make sense of that? Okay, so for example, is that, hey, from all of this, I want to know is what are the events that come from the database, or from the catch, if there was a catch hit or a catch miss. So you get the idea, and that's very mind blowing. Very, very mind blowing. So we don't have that observables natively. It is still in a draft. It means that we're gonna see Lang on the language perhaps in the next decade. Who knows? And that's why we focus our attention is on RxJS, which is made by Steve Keeney. And here Steve Keeney is trying to have a more practical approach on this, because here we're gonna see how can we create now is observables, how can we test that, how can we look to manipulate data in time with observables, and eventually orchestrating across multiple APIs. So because from the programming perspective, now think of RxJS as Lodash for events. Okay, so if you look at promise, which give you now an eventual value which fire once, observables will give you now a series of eventual values, right? I think this is quite beautiful. By see that as we now starting to have more challenge, not only in computer but in life, that at the beginning it start with one single stuff, and then once we need to scale that, how can we handle that, how can we deal with? So for example, if you want to have a fit body, so what are the things that you need to do to actually is deal with all of this, to achieve and maintain the goal, right? Which is pretty much what I'm doing here with an observable. Is this series of streams of data. In this case, you can think of this like days, all right, that are coming out through you. And that might be quite wild to think about it, but you can think of all of these different days that are coming through you, right? Day and night, day and night, day and night, day and night. And once you perceive that, you say, hey, I need to actually, if I want to keep my body fit, I need to do something in as this day comes in, or as this day comes in. Sorry. Now, so well, I'm gonna define an hour to eat and another hour to hit the gym at least. So that'll makes a lot of sense. Totally makes a lot of sense. So yeah, that's quite interesting, by the way. Very, very, very interesting. All right. So this is it. This is it. So the agenda here is what we're going to do. What we're going to do together. Get a conceptual understanding of what observables even is and what kind of problem you could possibly consider to solving. And get our hands dirty by playing around with some simple test cases. Build a few really simple applications using observables, and solve for some common UX UI using observables. And then he elaborated, Steve Kinney, a lot of this kind of stuff with the idea of why you are still employable as a UI engineering is because a lot of the UI, the API doesn't support that. So you actually, it's pretty much like legacy systems. It's legacy systems. So they need to find a way to make that API, okay, to support the UI. That's all. That's all. So you have to do a lot of bunch of Rube Goldberg machines in order to get the UI in place. So yep, let's get into this. Let's go to now actually look at the basics, right? Because this library is huge, massive. And then we're gonna get ourselves familiar with this. So create an observable out of one or more values, okay, and from, okay. So as you can see, is you can create now observables is from a series of values, primitive values, and from a anything array like or observable like this. So that's the subtle difference between the of and from, is that you can create now this sequence of data or this observable, okay, is a series of eventual values, okay. So you can create all of this series of eventual values, whether it's primitive or in a collections, all right, with an array like or an observable, but all of them are synchronous right now, right? And this is the way of how you can now listen to this. This is the deprecated version of that, okay? And now is the more updated version to go with. Perfect. Okay. So,
kind of what we might see more commonly, which is you can give it an object with next, error, and complete. And so in this case, if you only care about the errors, you give it an object with an error key. If you only care about complete, you give it an object with the complete key. If you only care about next, whatever, right? Whatever combination that you care about, you can subscribe to it and have those callback functions called. So the rule of thumb that we're going to kind of use here is if if you need an error or a complete event, we're going to use the object. Most of the times we only care about the next event that comes through, right? In that case, we can just pass it a function and move on.
So that'll be all for the video. Take care.